institute lecture by Professor Murali Annavaram. Professor Murali Annavaram is visiting us on visiting chair professorship. Visiting chair professorship is called the History of the Rukmini Sri Gopalakrishna visiting chair professorship. It was instituted through the support of a generous endowment by an alumnus. The alum wishes to remain anonymous to promote research in CS and in allied areas. We have had several distinguished visitors as part of this visiting chair professorship. I'll just read out some of the names. Richard Anderson from Washington University, Ivy Cartman from CMU, Michael Norman from UCSC, Rakesh Agarwal, who's the president and founder of Data Insights Laboratory, Sargur Srihari, alumnus and who's recently passed away, who was at SUNY Buffalo, and then Babak Fatsafi from PFF, Pavel Held from Simon Fraser University, now Professor Murali Annavaram from the University. And go forward to introduce Professor Murali Annavaram. Apart from his current role as the visiting chair professor, he is the Dean's Professor in ECE and CS departments of University of Southern California. He is also the founding director of Real at USC Meta Center that's focused on research and education in AI. His work at Intel led to the first three-dimensional micro-architecture design and influenced Intel's Turbo Boost technology. He's a fellow of the IISc and is also a half marathon runner. He ran the half marathon in Bangalore recently in October. With those few words of welcome, I request let's welcome Professor Murali Annavaram.
Good afternoon. It's in fact my pleasure to be here, and thanks for inviting me. And so, as the title of this talk, it speaks for itself. Basically, it's energy efficient computing in the climate crisis era. And for those of you who are wondering what the picture is, that's a picture of the Kolos data center that's actually being built in the Norwegian fjords all the way up in the Arctic Circle. And the reason why they build these data centers way up into the Arctic Circle is very simple. It's cold. And the reason it is necessary for it to be cold is because data centers consume massive amounts of energy, and that energy needs to be taken away from the data centers. Basically, they generate a lot of heat. And so there is a constant struggle to reduce the energy consumption of the data centers. And obviously, we can't take every data center and locate it into Arctic Circle and expect it to somehow solve our problems. And so that leads to the naturally, how do you build energy efficient computing systems so that we don't have to have all our data centers in the Arctic Circle? So that's sort of the focus of what we want to talk about today. So with that, let me start with a very simple rhetoric question, which is, how many of you have used at least two of the services listed here? I assume so, because in fact, even in a non-technical crowd, if I went and gave this talk, there will be 80–90% of the people who would have said, I would have used one or two of these services. And the reason why these services have become so popular is because they make our life very easy. And in order for them to make our life very easy, they run in what is called the cloud computing centers or cloud centers, which are basically large data centers. And the heart and soul of these cloud computing systems or cloud computing infrastructure are servers that are in these little blue things that are there. And these servers are the ones that are computing on massive amounts of our service requests and generating the right responses. And in the process of doing so, they also produce massive amounts of heat and they consume lots of energy. And so this is, it's not a one-time wonder. If you look at the cloud computing growth, when I started at USC roughly in 2007, it was about a $6 billion industry just beginning at that point in time. And in 2014, 6 years later, it basically went from $6 billion to approximately $78 billion in market size. And then sort of projected forward to 2020, you now have a $160 billion industry in cloud computing, and basically data centers are the heart of this infrastructure. And this growth doesn't come for free because these are very power hungry. And what I mean by that is that in 2013, if I measured the total energy consumption of all the data centers in the US alone, this was 91 billion kilowatt hours. To kind of put this into perspective, that's powering 2 New York cities for the power consumption that they use. And then if you project it out to 2020, it has grown to 140 billion kilowatt hours. And this is taking into account all the research and development that has already gone into making our compute infrastructure very energy efficient. And so they consume 140 billion kilowatt hours, and that's basically 3 times the New York City power consumption. And not only that, in order to generate that much amount of an additional electricity, you would need 16 power generation plants, and that's a substantial amount of carbon impact that these data centers are going to have. And so there's clearly a problem that needed to be addressed, and this problem existed, as you can see, from many years. And so the root of the problem, if you look at where the roots of the problem are, the roots of the problem actually exist in how CMOS technology works. And so CMOS is basically the most popular technology for producing computer systems today. All our transistors are built with CMOS. So all of our circuits are built with CMOS. And CMOS actually operates on 2 very well-known principles. One of the principles is called Moore's law. The other one is called Dennett's scaling. Many of you may have heard, particularly if you are in the computing space, what is a Moore's law. It basically says that every 18 months to 2 years, the number of transistors in a chip will double. So basically, the density of the transistors will continue to grow. Then the not so well known, but actually, in my opinion, even more important is Dennett's scaling. Dennett's scaling says that as the transistors become smaller and smaller and your CMOS technology, their voltage, which is required to operate them, can also be lowered. It's one of those beautiful things where you can actually make things smaller and also reduce the energy consumption at the same time. And you get basically one of those few scenarios where you get to cut your cake and also eat it too. And that obviously, not many good things last forever, and this is also one of those. By around mid-2000s, this Dennett scaling started to see the first impact where you could no longer reduce the operational voltage of these systems. And as a result, you can produce lots and lots of transistors, but they continue to now burn as much power as they each on a per transistor basis, just as much power as they used to burn before, because the Dennett scaling slowed down. And as the Dennett scaling slows down and the density continues to increase, we're basically asking for trouble in terms of energy consumption and in terms of just the heat that they generate. And so basically, density without Dennett is sort of the root cause for many of the computer system problems that we see today. And so naturally, this is a problem that has been identified by many, many people. And so there are many, many people who have worked on this problem for many years. And what has been done, and this could go on, I could give you a whole semester lecture on what are the energy efficient techniques people have worked on. But basically, people have looked at clock gating techniques, voltage power gating systems, and things like that. If you didn't understand, it really doesn't matter as much. But basically, people have worked on various variety of technologies to reduce the energy consumption of these systems. And what, as a result of that, is that in today, you can compute approximately 1 billion floating point operations, let's say 1 billion multiplications on a single joule of energy. That's where we are at this point in time. And so we'll say, hey, 1 billion computations for a joule of energy, what the heck are we complaining about? Aren't we really good with respect to the energy efficiency? What's all the fuss about? But if you look at the graph that I plotted here, which is basically the machine learning models over time, how much petaflops of energy of computation that they needed to train those models. And this is basically growing at an unimaginably fast pace. So you are into the thousands of petaflops of computations. And by the way, flops simply means number of floating point operations per second that these systems have. And so these are huge compute demand systems. And so our appetite for computing is not saturated. We are continuing to take as many compute that you provide. I need it more, I need more, I need more. So we are sort of greedy because we want to digitize the whole world to the extent we can, because there are substantial benefits to the society when we digitize systems. And as a result, this is not going to be enough. And so, given that sort of a framework, what we have is a balancing act from the industry. So basically, industry is trying to do two things. One is improve the efficiency of the cloud servers itself. And the second one is shifting away from frequency runs to more what is called chip multiprocessors or parallel processor systems. So these are the two things that they have been working on. And what I wanted to do in the rest of this talk is to talk about what my group has done over the last, I would say, about a decade and a half or so on helping the industry sort of tackle these two sides of the issue. And so let's talk about Act 1. The Act 1 is going to be improving the energy efficiency of cloud servers and how one can improve these cloud server energy efficiency. And so it turns out, why is building efficient cloud servers so hard? And again, this is actually the aerial view of the same data center that is being built that I showed you earlier on. And it turns out that it's actually, not to demean the architects, but it's actually a little easier to build beautiful looking data centers than to build computer server systems that are actually energy efficient, much more challenging problem. And so the question therefore is, why is it hard? And there are multiple reasons, but one of the most common reasons in data centers, particularly or in the cloud infrastructure, is the utilization problem. So what in this particular graph I'm showing you is the number of requests that are received by a Wikipedia single server in the Wikipedia cloud that is processing the request. I'm sure all of you or many of you must have used Wikipedia to get some information on the web. And the number of requests can range anywhere from about 2 requests to about 20 requests every second on a single data center. So two things to note here. One, there is no second in this whole infrastructure, in this whole time window where 0 requests come in. There's always some amount of activity happening. And there's a substantial amount of periods of time where you're only receiving 5, maybe 6 requests, not the 20, 30 requests that you see. And therefore, these systems, these cloud systems, are operating essentially at a point where they are producing 5, 6 queries a second, although they are actually capable of producing 20, 30 queries response times in 1 second. And what that means is that these systems generally are operating at a very low utilization in cloud. And that has been proven multiple times by many, many companies, including Google and so on. And the flip side of the problem is that if you look at the industry, whether it is Intel's or the AMD's or the IBM's, what they have done is that they have focused on improving the efficiency of the systems at the two extremes. If your system is idle, which means 0 requests, not 2, not 3, not 1, 0 requests, then we can shut down. You've seen your laptop go to sleep, and all the machines will just continue to sleep if you don't do anything with them. Or if you're running a mega maniacal GPU game on your laptop, the system is reasonably efficient. That's what people have done. But what industry has forgotten is that these cloud systems tend to not operate at these two extremes, but they're actually operating in somewhere in the middle. And in that middle zone is where the efficiency did not improve as substantially as one would like. And I will show you some quantitative data for actually demonstrating this. And therefore, data center servers are rarely operating in these two extreme regimes of fully operational or idle operations. And so you are kind of trying to figure out how these systems are going to do in this intermediate utilization. So if you now look at the peak power consumption, this is the measured power on a real system. On the x-axis, I'm going to show you the utilization as you increase the amount of work the machine is going to do. And on the y-axis, it's the percentage of the peak power that this machine is going to burn. So this is how the machine actually, this is a machine something around 2005 timeframe. So you can see the machine's power continues to increase as you increase its utilization of the system. And if you look at the efficiency of the system, its efficiency as measured in, let's say, number of operations per watt of energy, this is how the efficiency of the system looks like. It looks extraordinarily terrible at lower utilizations because it burns a lot of power without doing any work. And therefore, the efficiency goes really, really poorly. And eventually, the efficiency reaches whatever is the peak efficiency it can achieve. And so this picture already tells you the story where the problem lies. And the problem lies exactly here, which is The typical operating range of most of the computing systems is right here, and this is the region where the efficiency of the systems is extraordinarily poor. And as a result, you are going to see your data centers burn and burn a lot of power, even when industry put in a lot of effort to optimize that point and optimize the idle point. So these 2 points are sort of the wrong focus from a cloud data center operating perspective. And so ideally, what we want a system to do is to do like this. As the utilization grows, the power consumption should grow linearly with the power. And this is what is called a perfectly energy proportional system, a system that actually burns power in proportion to the utilization that the system is going to go through. And so this is what is called a perfectly energy proportional system. And in this system, if I measure the efficiency, which is the number of operations that I do per watt of energy, it would look fantastic. It would look unchanged. It's 100% all the time. And this is the idealized system that we would like to build for these data centers, so that no matter where you are operating, you will always get the best energy efficiency in these systems. Yes? Okay, so for those of you who are on the teams, so the question is this data specifically for a homogeneous set of cores in your server, or is there heterogeneous cores that are actually operating some low power and some high power cores? And it turns out that in around 2005, 2006 timeframe, when we were starting to do this work, they were all entirely homogeneous systems at that point in time. All right, so this is basically what we are going to try and look for, which is basically look for systems that can be built which have a perfectly energy proportional nature to them. And I wanted to highlight this important point for those of you who are thinking energy efficiency is the same as energy proportionality. I want to say that they're actually not the same. Energy efficiency and energy proportionality are slightly different metrics, and this is actually a fundamental disconnect to many people who work also in computing systems. And what is energy efficiency? One simple method is just to say how many operations per joule of energy or per watt of energy that you plan to burn. And this is typically measured at peak utilization. So if you have gone to the supercomputing center at IISc and you look at the supercomputing center statistics, they usually say it can do 5 petaflops, 20 petaflops, whatever that number that you see is the peak utilization. If every machine is allowed to do the peak of its computation, that's the amount of throughput that you're going to get out of that machine. And that's what is called the energy efficiency, which is measured at peak utilization. But if you look at what energy proportionality is, it is actually measuring the efficiency across the entire utilization space, not at just the peak or idle systems, but across the entire system, across the entire range of utilizations. And so this is basically the issue, is that most people confused energy efficiency to mean simply energy proportionality, and therefore when they operated only at peak or idle, they said we are done, we have done a good job. And so one of the first things that we have done in my group is to let's measure the energy proportionality. Let's actually look at what the systems have done over all these years and see how energy proportional these systems are. And so when we started this work, one of the most common ways to measure energy proportionality is one of the metrics that I'm going to show you. But before I present the actual metrics, I want to kind of give you a couple of things to ponder about. These are 2 servers, A and B, and we measured the power consumption as the utilization is increased from 0 to 100%. And these are the 2 curves. These are actual measured curves of these 2 servers, A and B. And so this is the empirically measured power usage across utilization. And this is a linear extrapolation between the idle and fully utilized systems. And this is what we call the ideal energy proportional system. That's what we really want to build. And so let's say that we have these 2 servers, and then you say, well, I got some work to do. Which machine should I buy? Should I buy server A or should I buy server B? And so one approach is to say, let's measure the energy proportionality. And one way to measure the energy proportionality is to say dynamic range. This is a very commonly used metric, which is basically peak power minus idle power normalized to the peak power. Basically, it's just a fraction. And it's basically looking at these 2 endpoints and measuring what that is. And that is what is called dynamic range of the systems. And so if I look at the dynamic range of these 2 systems, it turns out that the dynamic range of the system is 60% and the dynamic range is 50%. So, hey, good, this is a good system. We should buy this system because it has a better dynamic range than the one on the right, and we say this is a good system, let's go buy it. And then it turns out that when we put it into your data center, let's say we put it into a Google-like data center, which is processing Google-like workloads, it actually turns out that server A, which is supposedly more efficient, consumes 68.6 watts of power versus server B, which is this, consumes 64.6 watts of power. And you wonder, oops, we thought this is better, but in a Google data center, this burned more power than the other one. And then you say, why? What was missing in this system? And obviously, I have given you hints already. The hint lies in the fact that if you look at just this utilization range, which is where most of the operating point of the systems are, this is actually burning more power in the low utilization range than this system on the right. And that's the fundamental problem.
All the load, few machines and shut the others off.
Good question. So the question again for the teams people is that can we consolidate the work so that you always push as much work into as few servers as possible, so that we can idle as many systems as possible and take the few operating systems and operating systems as in systems that are operating and run them at the peak utilization. That's, seems like a good choice, except that choice is not what most data centers would consider today, simply because when you click on your Google search and it takes you more than 0.15 seconds, you are unhappy. And the reason is consumers have a very short time window before they are willing to accept any longer latencies. And as a result, most data center operators are very worried about losing their customers, because there is when you're moving these workloads, it doesn't come for free. It has a cost associated with it. And as a result, for operational efficiency, when I mean operational efficiency in terms of user happiness, typically they don't like to fully maximize my utilization, because if there's a sudden burst of inputs coming in, you can't handle that because it takes time to bring up the machines at that point in time. Yes, and in fact, that's not even a parameter to consider. It's users are the gods, right? For these companies, there is no such thing as, oh, let me compromise some user quality so that I can save some dollars on the electricity bill. That's not a choice that any company. I worked for Google, Intel, and Meta. We wouldn't consider those at the times when I was there. And so I think that's the problem that is fundamentally what we're looking at. Okay, so this is a problem. And so let's now look at how can we accurately quantify the energy proportionality of the systems. And so basically we said, let's look at a different measure, different way of thinking about energy proportionality. And the way we think about energy proportionality now is the area between what you think is an ideal system and the actual system's usage of energy itself. And so if you look at this area between this dotted curve and the blue curve, and that subtracted area, that is the area that we are going to consider to be energy proportionality. And therefore, the smaller that area, the better that system is, right? It makes it now intuitively obvious that that area should be minimized. And so that's what is the 1 minus that area is basically trying to minimize that. And that's basically energy proportionality. And if I apply that metric, suddenly this system actually looks worse than this system on the right-hand side, which then matches your original intuition that this is actually going to be better for your Google kind of workloads. And so this EP is a better indicator of energy usage than dynamic range. And then you say, yes. Okay, so the question again is, system designers over time have gotten better at improving the efficiency at idle systems. Therefore, at 0%, they should be consuming 0. But and two things. One is they don't consume 0. You know that already. If you just close your laptop and do nothing, you expect your battery to last infinitely, right? Assuming that your battery is not losing energy due to other environmental reasons. No, your battery continues to drain even if you don't do any work. There are many reasons, one of which is that fans, you turn off the machine, but the fans are still rotating to cool the machine. There are network packets coming in. Your machine is constantly talking to people, even when you shut it down. So there's always a certain amount of activity, and there are voltage regulators that are just simply not so great. And so the variety of reasons why the utilization at 0% utilization, the energy is not, or the power consumption is not zero, but it is, at this time, it was in this machine, it's about 30%, 35%. But now actually many systems have gotten to like about 20% or so. Oh, this is, as I said, it's a long historical trajectory that we are looking at. And so EP, it turns out, is a better indicator. And then the next question to ask is, what was missing in dynamic range? What was the problem with the dynamic range itself? And the issue is that the dynamic range is not enough, because EP is basically how linear is the power curve on top of the dynamic range. That's really what was the aspect that we needed to capture. And so we introduced this notion of what is called linear deviation, which is again a very simple formula, which is the actual area by the linear area, which is this area. And then we basically say that this is what is called the linear deviation of a system. And by that metric, all the systems can be classified into three categories: a perfectly linear system, a superlinear system, and a sublinear system. A superlinear system will have a positive value of LD, and a sublinear system will have a negative value of LD. And so it is obviously, again, I want to sort of give an intuition. Basically, what it is showing you is that, is your blue line kind of, you look at this linear line, is it below or above on average, across the whole spectrum? And if it is above, that's bad. If it is below, that's actually better. And what it is saying is that if the linear deviation is negative, it simply means that it is actually burning less energy in this intermediate operation regions than when you are actually doing its operations at the peak utilization. In other words, these systems, again, to sort of summarize, these systems somehow are tuned to work better at intermediate utilizations than at peak utilizations. And that's what is called a sublinear system. And so the natural question, therefore, is to my machine froze. 1 second. Yeah. So the LD basically is what we are actually interested in. And so given this matrix of information that I showed you, what I wanted to do is basically, let's look at what the metrics that I gave you: energy proportionality, linear deviation, and see how the systems have fared over time. So we picked up 291 machines that were produced between November 2003 and December 2007. These are every machine that has ever actually been produced. There are 291 servers that are actually produced. And we measure the power consumption at various utilizations of all these 291 servers that are there, right? And it turns out this is how the dynamic range looks like. And each one of these dots is one of those 291 machines. And this is the dynamic range. And this is the time window as we progress. So industry actually made progress, right? So you went from about 40% dynamic range closer to about 60, 70% dynamic range over time. What that means is that people have actually spent time optimizing the two endpoints so that the machines become more and more efficient across the two endpoints. And so it has improved from about 50 to close to about 70 to 80%. You can see those data points. But from there on, the dynamic range stalled. And today, dynamic range is almost impossible to get it to 100%. A 100% dynamic range system will consume zero energy when it is zero utilization. But that such system doesn't exist today. And the variety of reasons that I just mentioned before: power supplies, voltage converters, fans, chipsets, networks. There's a whole host of things in your system that are just going to burn power even if you do nothing with them. And so that's the dynamic range trend. Let's take a look at the EP, energy proportionality metric trends. And what I did was I took all the 291 servers, and then I classified them into superlinear and sublinear systems, and I plotted them across time as shown here. And if you look at the EP, basically the high energy proportionality servers all tend to be minus LD machines, or basically sublinear machines. And hence, what we noticed is that the few systems that existed out of this whole 291 that did well tend to be sublinear systems, because they're optimized for running somewhere before they reach the peak utilization. So their efficiency is achieved before they get to the peak itself. And so these are the systems that are basically sublinear systems. And so since the dynamic range growth has stalled, the only way to improve the energy proportionality is by lowering the LD. So basically, you take your common operating regime and try to hammer the system into doing the best it can within that narrow range of utilizations where the system is going to be used. And so that's really what the goal of this of the systems are going to be. And so we then said, okay, are the systems already doing that? What I'm plotted here is the efficiency of the systems measured in some number of operations per watt when it is operating at peak load, 100% utilization, and then operating at 10% utilization for all the systems. What you see here is dramatic. The systems, when they are operating at peak, have actually gotten better and better and better over time. But if you look at the efficiency at the low utilization range at 10%, they have not improved very much. And so what this is saying is that to some degree, industry got blindsided by the fact that let's optimize for the peak utilization and optimize. And so they got it really, really well. But at the low utilization range, they did not do so well. And this is the reason, it's sort of the roots of the evil that I was mentioning, is one of the big roots of that evil. And so the high energy efficiency at high loads is grown dramatically, but at low load has grown slowly. And most data center workloads are actually spending their operational intensity in this regime, 10, 20, 30%. And so we need a low utilization energy efficiency growth must be addressed to actually build a new system, a new way of thinking about this system design. And so we are going to start thinking about overcoming this energy proportionality wall. Yes. So industry actually knows, like, for example, if you look at Google's own internal data center utilizations, they actually publish results. They know what the average utilization trends look like, for example. But as an end user, you and I may not know, but most of the industry server designer, when I say industry, I should be careful. The cloud industry people know what their operational utilizations are for these servers. Exactly. In hindsight, things look so obvious. And in fact, that's exactly where we are going to go. And in fact, you kind of somewhat preempted what I was going to say, but I'm glad I got the point across even before I got it to you. And so basically, we want to improve the future servers by improving this linear deviation metric. And therefore, we need a mechanism to exploit the intermediate utilizations to build new systems. And hence, there's now a need for what we call, and this is in 2008-9 timeframe, what we call server level active low power modes. In other words, these are low power modes that allow you to be active, right? Inactive low power modes, people know how to build, but active low power modes, people did not know how to build. And that's a fundamental problem. Yes.
The case, some servers are underutilized, some are overutilized. The total is relatively cross servers.
So I don't know exactly how individual server utilizations can vary, but the metrics that I showed, which is the 20 to 30% utilization, is the across the spectrum of data centers, cloud servers in a couple of racks. That's what your utilization actually averages out to be on all these machines, and therefore I don't have a precise metric for each server how it actually changes. I mean, one could say that there are small variations across time, that some servers are really busy for a short period of time and some servers are idle. But it is fair to say that on average, this is the behavior that you see. And when I say average, I'm not talking about like an all-day average, but I'm talking about like within a minutes of average, because these machines are actually changing their operations very, very fast in a very short, narrow windows of time. And so within a short window of time, you see that natural 20–30% utilization of these systems. And in fact, if any of you are working in supercomputing center, go measure your supercomputing centers efficiency, and you will be surprised that they will be in the 20–30% range even today. Even today.
Communication across servers, in other words, because latency is so important, does it mean that forbidden, no one to
Move
data?
I think that's similar to Professor Rajesh's question, which is is it possible to move the work to consolidate and maybe get a better utilization distribution across the machines? But it really has a penalty associated with the latency, which is when you move work, particularly today's systems are very, very stateful. What that means is that any query that I run has a lot of state associated with it. So for example, you are typing in your Google query, it's auto-filling what you're typing in. It's because it's actually recognizing what you're actually filling in. So there's a lot of state built into these systems. That's just one example. And the search queries, it may not come to a surprise to you. If you searched 5 things, all associated with Bengaluru, 6th query will automatically try to focus on Bengaluru without you actually suggesting it to be Bengaluru. And hence, it's very important that these systems actually have that state to improve the user efficiency or user utilization. But in the process, this moving of the data is very expensive. Yeah, so the power that I mentioned is purely computational power. And so the question I think for the Teams people is there a data communication cost I included? Because I'm only looking at a single machine and what its power consumption is at different utilizations. So honestly, I don't know the exact answer with respect to the network energy consumption and network related energy proportionality. That's something that we haven't studied. We looked at primarily compute systems as individual systems perspective. Okay, so basically what we wanted is a server level active low power mode. That's what we wanted to design. And that led us to the first system that we built called the night shift. So this is a system that we actually built. It has a lot of wonderful secondary meanings to it. Basically, night shift, for those of you who are familiar with burqas in the nighttime, monitoring your house for security without you wake up all the time. That's one example. But the night is also an example from a perspective of in the old British system, knights used to go to the war before the king actually gets into the war. And so there's lots of scenarios where night is actually employed to protect the primary person from the harm on a daily basis. And in our more mundane life, there is lots of administrative support who handles our phone calls, our emails, or other kinds of things, so it doesn't get disruptive to you all the time. That's exactly the kind of a principle which is called night shift that we have applied. And so what's a night shift system? Night shift system is basically a server level active low power mode solution which utilizes low utilization periods. This is the key. If I can underline something and I want you to take away something, this is basically the low utilization period. And the basic idea, as you have preempted me, is to look at fronting a high power primary server with a low power compute node called the night. And the night is going to be responsible for low utilization periods, and the primary system is going to be responsible for the high utilization periods. And so we now built a system called a night shift system where there's a big server and there is a small night node, and the night node, the primary server and night node are independent in our implementation of the systems. There are different ways of building. And then they have independent power domains, they share a disk, and they have a network routing protocol that allows each of them to ping each other and wake up each other and put each other to sleep. And this entire system is actually fully prototyped and actually demonstrated in one of our demonstration prototype systems and to industry folks. And so this is the first system that we built. And how does this system actually operate? It should be obvious now what it looks like. So basically imagine that you have the primary server and the night that are actually in, and from an external software perspective, I should make it clear, they think of it as a single system. They don't recognize that there are multiple systems kind of hidden underneath it, basically these heterogeneous systems. And so when the primary server is operational, initially its utilization at some point goes low, it flushes its state and tells the night to actually start actively taking on the requests. And so the night will basically start acting up and start acting on the requests and start to do computations. And so it becomes processing requests. And what happens at some point is that the utilization grows high, and then it wakes up the primary server and says, hey, you need to handle it. I cannot do it. And then the primary server wakes up, sends a message to the night. The night will then handle the request, hand over the request back to the primary server. And this kind of goes back and forth, ping-ponging across the systems. They share resources, and this is where our design is really good at, is that it doesn't need to move these large amounts of state between these systems. And so the questions that Professor Rajesh was asking, which is, can I move all this computation and the data associated with the computation? We don't have to, because it's integrated into a single motherboard, and they're kind of moving back and forth between these systems. And so this is the entire design of the night shift that we have built. Yes.
Gradual shift primary server to the second server, but it looks like you're holding up computation before you move to the primary server. That has other complications.
Yeah, so I think the question is there a way to move this across spectrum slowly, as opposed to like abrupt switches between the night and the primary server? There are many ways to design this system. My student need to graduate, so we built a system that is reasonably easy to build before he graduated. It's 6-year window. And so it's more of a practicality rather than the actual, the principle itself can be applied broadly speaking, actually. Correct. Yeah, so it doesn't involve any large software stacks and such. I mean, I want to make sure that we understand, because this is an academic project, not an Intel project. There are certain simplifications that we did, which is, how do you build, like, for example, not shift abruptly? You could do this more efficiently. And in fact, this is basically what we propose, which is called these night shift systems, which is high and low power. And lo and behold, 2 years later, ARM introduced Big Little. For those of you who are familiar with ARM's Big Little infrastructure, Big Little infrastructure is exactly this idea, which is when you have lots and lots of heavy duty computations, you take those 2 big cores and then you hammer on them. When you have lots and lots of small amounts of work to, you just allow the little cores to do that work, and you can kind of move back and forth with the system. And so 2 years after we built this, ARM actually introduced Big Little.
It looks like there is other cost. Here the focus is energy.
Correct.
You have second processor now.
Yes, so there is a cost. Yeah, so the question is this, so there's total cost of operation, the TCO cost is this question that Professor Rajesh is asking. And it's an interesting question. It turns out that these little nodes that we are building in our infrastructure that we built, the primary server costed us approximately $3,000 at the time. The night node which we built, which is a small motherboard with a tiny Atom processor, was approximately $50, right? And so it's not zero cost, but I believe this can be cost efficiently built in practice. And in fact, ARM question can be applied to ARM's Big Little too, because it builds this complex infrastructure where there are multiple big cores and multiple small cores. And in general, only one of those 2 sets of cores are actually operational. And so one could say, isn't this cost operational? It's the same argument that they also made, which is the cost of additional small cores is relatively not that expensive. And so what happens if you apply night shift to our server, that beautiful server A that I mentioned to you, then now the system would operate like this. Up to a point in time, the night is actually operating, and therefore the overall power consumption is tiny. And then this abrupt shift that I was talking about happens at the 20% utilization. Why is this? Because the night is 20%. Because we can design the night to be capable of handling certain number of requests with the relationship to the primary server. And here it is a 20% capable night, and hence it shifts abruptly at that point in time. And we said, let's take a hypothetical study, and let's say that we can convince Intel's, AMD's, IBM's, and everybody to build a night shift. Every system will be a night shifted system. And so we're trying to convince the industry at the time that you folks all need to build ARM's Big Little equivalents, right? And so we said, well, let's take all of your servers and we make them night shift enabled. everything beautifully moves to the left, and everything becomes sublinear systems, and all the servers will have an EP greater than 60%, and some servers even achieve perfectly linear energy proportionality in these curves. And so we also prototyped it. We actually demonstrated it to multiple companies. We ran a Wikipedia workload directly on our servers, and as the workload shows you, and I've explained to you what the workload is, the number of queries coming into the system. When there's very little work, the night evaporates, and therefore the power is very small. When the workload increases, the primary server kicks in. When the workload decreases, the night operational comes into play, and this whole system is completely automated, and it can actually be used. And the beauty of this project is that we can actually demonstrate with one graduate student's effort that so we burned 23 kilowatt hours of energy on a single one-day operation of this machine. And we took that, it's a one-day trace of Wikipedia, one-day trace. And then when we night shifted that Wikipedia server, we burned 15 kilowatt hours of energy. That's 35% reduction in your total energy consumption. So if you have a $100 million electricity bill, that's $30 million in electricity bill saving, not to count the air conditioning costs and not to build all the way into Arctic Circle either. And so it's a substantial benefits that one can actually achieve with these systems. And so this is the work that actually won the most influential paper award a few years ago, and we have demonstrated this to multiple people, multiple companies, and such. So, yeah. Correct. It's a more of a business question than this is what we showed. It says, hey, if you pay 19% latency penalty for your, remember that this is tail latency, right? Like 95th percentile latency, not the average. Average is very little change. 95th percentile, some requests, and you can see why it is, right? Like when I'm trying to shift directly to this zone, suddenly requests come in and they're like, oh, shoot, I don't have the system. So it is what it is. And so we have demonstrated this, and there are ways to solve this problem, right? Like instead of having a single night, I can have night 1 and night 2 and night 3, and I can kind of move through, which is exactly what ARM's new heterogeneous cores are doing, is that they can go from operation point 1 to 2 and then to the full load of the system. So heterogeneity can give you that flexibility or the elasticity in the system itself. Okay, so let's now shift our gears to the balancing act 2, which is basically shifting away from frequency to chip multiprocessors. Basically, industry has been looking at trying to build efficient data center servers. And if you are, I mean, many of you are pretty young, but if you are at least in my age group in the mid 90s to early 2000s, Intel processors would always come in your advertisements that say 750 megahertz. You may think it's really slow, but it's actually quite fast at the time. Then 1 gigahertz, 1.2 gigahertz, 1.5 gigahertz. So that was their marketing mantra. That is what they used to sell computer systems, gigahertz. But if you look at computing advertisements today, hardly you can actually find the gigahertz anywhere mentioned in these systems. In fact, you have to go into a technical document to see what frequency these systems operate on. Instead, they build what is called chip multiprocessors, which is multiple processors built into this single core, and that's the shift that has happened. And what I wanted to show you is that when you do the shift, can you do the shift without destroying our existing software packages and existing user satisfaction measures? And that's basically my act 2 of this talk, which is going to take a few minutes to describe. So why shift away from gigahertz to CMPs, or chip multiprocessors? It turns out that from an electrical engineering standpoint, it's very easy. As you increase the frequency, the power consumption is has a cubic relationship to the frequency. So what that means is that if I increase the frequency by 2x, your power consumption will increase by 8x. And that's, that's a basic EE 101 kind of a lecture where you have CV square F, and F and V are proportional, and therefore every time you double the frequency, your entire power consumption will be increased by 8x, right? But in practice, it's not exactly cubic, it's approximately squarish relationship because you can do some optimizations. But basically, this is a cubic wall. And people climb that wall. You can actually see over time from Pentium Pro to Pentium 4, they climb that wall. And it got extraordinarily challenging, right? Like you can climb Nandi Hills, maybe the next hill on the top. Eventually, you'll get to Everest and say, I can't do this, right? And so that's exactly what happens. And basically, you can no longer climb these huge walls. And so we take the opposite approach. The alternative approach the industry took is called the chip multiprocessors, where you design a nice processor and you just copy it 2 times, 3 times, 4 times, 6 times, 8 times. Now there are approximately 80 cores on a single system or a single chip. Why is that better? Because it's a linear increase in the power. There is no cubic relationship in that case. You take a power of a single core, you put 4 of them, the power only increases by 4x. But if you can actually use all the 4 cores, you get 4x performance improvement. It's like quadrupling your frequency without actually getting to the 2 to the power relationship, 2 to the power 4 relationship on that particular problem. And so it turns out that this was considered to be a good way to handle, basically build more and more chips or more and more cores on a single chip. And we said, let's ride this wave now. And so there was a period of time when people were thinking about multiple cores, multiple cores, multiple cores. And it turns out that when you're trying to do multiple cores, it's actually okay, but it is not possible for 1 million chimps to actually create one of the most beautiful ragas, Raga Nalinikanti, because you sometimes need that 1 billion mind. As equivalent in it's kind of connecting it back to our work, it's like basically saying that I have thousands of cores and each of these cores is going to do something interesting and then somehow magically the greatness will appear. No, it doesn't appear. For those of you who write software, you know that it's extraordinarily challenging to parallelize software. And therefore, it's not easy for you to use these hundreds and hundreds of cores and somehow magically achieve that 8x improvement or 16x improvement in performance. And so this is what is called Amdahl's law. Amdahl's law, for those of you who are not as familiar with, is basically a very simple principle that basically says that imagine that you have a software where 90% of the software is highly parallelizable. You can do all kinds of optimization, make it really, really fast. And in fact, so fast that it can be done instantaneously in 0 time. But your 10% is still behind you. And therefore, the maximum performance that you're going to achieve is going to be limited by that one sequential piece. And therefore, you'll get like a 9, 10x performance improvement and nothing more. And so this race towards multiple core systems caused us to wonder whether this is going to hurt the performance of actual software. There is a substantial amount of it which is sequential. And so that is the primary hurdle that we were trying to understand. And so if you look at what does it take to build a processor that can run serial code, and you look at a processor that can run parallel code, they are very conflicting in their demands. Serial processors tend to be beastie, very speculative, lots of memory, lots of speculation built into them. Parallel processors tend to be very simple, very easy to build, very easy to replicate. And so you have to kind of make a choice between very fast single core system, very high frequency, lots of speculation, or many small cores. And then you have to figure out how to parallelize your workload, like the 1 million chimps in this case. And so this is a very difficult trade-off to make. And so what works for serial doesn't work for parallel, and what works for parallel doesn't work for serial. And hence, how do you deal with a system? How do you build a system that works for both of these regimes? And that was the goal of our work. And that led us to building what is called EPI throttling systems, or EPI throttled systems. This was a work that actually eventually led to the Intel's Turbo Boost technology, which is now every single machine that you use has that. And AMD has something called Turbo Core, essentially the same principle, and so on and so forth. And so basically the idea is very simple. When you're executing a serial code, run it on a big core, one big core. When executing only 2 threads, execute on 2 medium-sized cores. When executing on all 4 threads, move that into 4 small cores. And kind of give you an animation, imagine that there's a single thread, run it on the biggest CPU that or core that you can get. And if your core suddenly has 4 parallel threads, because this parallelism is varying as it executes, the code is executing. And so when you get 4 threads, you basically run those on 4 small CPUs. And eventually when the parallelism reduces to 2, you run them on 2 medium-sized cores. And this is what is called asymmetric multiprocessing, which is also and another term for another way to achieving it is the turbo boosting was one way. And so for those of you who are not as familiar with turbo boost in your existing Intel laptops, what happens is that if your single core is, if only one core is running and all the other cores are idle, they basically kind of take away all the power that is given to the little cores and give it to this one core and boost its frequency and performance so that that one core can do the one task very, very fast, so that this power consumption of these little cores is actually essentially you just kind of grab or steal their power dynamically as needed. And that's basically what is turbo boost. And that's exactly what was implemented in our system at that point in time. In the interest of time, I'm going to kind of skip over some of the details, but basically we built this system extraordinarily well. And so now, as a result of this, basically Intel's turbo boost and turbo cores are all very popular. They originated from some of the work that we have done in this space. And as I mentioned, the ARM's Big Little is also is in relationship to what we have done in the early part of the work that I was mentioning to you. And basically, as I think you mentioned, rightly pointed out, the future is heterogeneous. It's not possible to build efficient, homogeneous systems. You have to customize, tweak, make those heterogeneity part of your design. And that is actually now extremely obvious. Every system, every computer system manufacturer is looking into that. And now, to conclude, basically computing is a tool for solving energy crisis, but computing itself cannot become a victim of large amounts of energy consumption. And energy efficient computing requires this multiple cross-stack design efforts. And new energy efficient technologies are in fact being developed and being the horizon. And for those of you who are interested in looking at this picture, this is an oil rig. If you actually are successful in reducing the substantial amount of oil we use to produce electricity, we can make them into livable houses as depicted by this artist in one of the futuristic system where you don't have to build, you don't have to use oil rigs all the time to consume the amount of energy that we do. So with that, my acknowledgements goes to my research group. And the work that I did with API throttling is with Ed Grohosky and John Shen. And Daniel Wong, one of my early PhD students, worked with me on night shift. And at IISc, I have been really fortunate. I had a great time already. I've been here for about 6 months. Professor Govind, Professor Vijay Kumar, Chiru, Rajesh, Arka, the list goes on, have been extraordinarily warm and welcoming to me and my family. So it's been a really great honor. And of course, also to the people who have funded my endowment support. It's been my pleasure to be here and be spending a year at IISc. So with that, I'll stop. And if you have any further questions, I'm happy to take.
Let's thank
Okay.
any online questions?
Is there any questions on the Teams side? If you can, please ask now.
Yeah, good afternoon, Professor.
Ah.
So I am from power electronics background. I'm a faculty in electrical engineering department. So I'm curious about this small CPUs you mentioned, right? You will divide the whole process between large CPUs, medium CPUs, and small CPUs. So from the power supply point of view, does that mean that we'll need low power point of loads for smaller CPUs? That's the idea.
Yeah, it's a good question. So I think the question you're asking is, do we need equivalently heterogeneous voltage regulation systems, for example, so that the small cores get a slightly different power delivery capabilities than medium cores, and the medium cores will have different than the large cores. So there is a whole plethora of, I mean, it's below my area of expertise, which is computer system design, but there is a lot of interesting work that needs to be done in power delivery, power management, whether it is voltage regulation and other kinds of technologies. And so there is certainly a lot of value in those. And I believe some of it is actually already implemented. If you look at existing on-die voltage regulators for CPUs, they use on-die because they can actually modify and make changes more efficiently and fast.
Right. Yeah, so basically with this architecture, since the processing is getting distributed, so what I suppose the distribution of the power delivery architecture is also expected to support that, right?
Correct, exactly.
Okay. Yeah, thank you, Professor.
The hall,
Yeah, so the question from the hall is, are there other things beyond, is energy proportionality the golden duck, or is there something more to do in the systems? And the reality is that there are many dimensions which one could work on with respect to energy efficiency. We tackled energy proportionality because we believe that cloud computing systems really need to tackle the energy efficiency aspects in the intermediate utilization, and energy proportionality seemed like the right direction to go. But there are fundamental advantages or techniques to actually lower the energy across the entire spectrum of utilizations that one could actually work on. Optical electronics. So the question is, does optical electronics play a role in sort of the future systems? And in fact, I gave a talk at the quantum computing lab about a week or 2 weeks ago, where I talked about some new technologies that we have been working on in the horizon, one of which is superconducting electronics. And I mentioned in that talk that optical electronics is one of the space. There are, again, I'm not an optical person, so I don't want to make unnecessary claims here. But in general, my understanding is that there is a lot of challenges also in optical electronics with respect to doing large sorts of computations, and there may be other issues with respect to. So in general, multiple things will move simultaneously, and at some point, one will overtake other, or there's some sort of a merger that happens in these systems. And so who the winner eventually will be, I don't know. But at this point in time, there's a substantial effort in post-CMOS computing, which is what can you do that is not transistors, not based on CMOS-based transistors. And so optics is one domain, because there are certain aspects which it is actually already used, right? Like, for example, if you look at InfiniBand switches, they're all doing optical electronics in some sense. And so there are some narrow spaces where it's already used.
You are talking of energy. There is difference in climate change and energy. Some of the algorithms can cause so much of climate change and so on, like AI and other. Are you considering those things also?
Yeah, so the question is energy consumption the only reason for climate change? Are there other algorithmic modifications that could actually worsen? So a simple example, for those of you who are more in the computer science, there are different ways of doing sorting algorithms. Some of them have order n square complexity, and some have order n log n complexity. So if you do something that is going to be n square complexity, it is going to burn a lot of power. So there are algorithmic changes that have to constantly evolve and improve in terms of order complexities of these systems. And so, but the question, I think the main point I wanted to make is these computer systems are no longer, oh, there's such a small part of your total energy consumption that they can be ignored. No, they are actually substantial in their total energy consumption. And therefore, they must, in fact, be tackled, whether it is done through algorithms, whether it is done through some of the techniques that I presented. It could be a mix of all of them, but it has to be tackled.
So I'm guessing in order to efficiently visit the code auto-parallelizing triggers that will go into the code on the good number of threads for different regions. Because leaving it to the programmer, open up the programmer means either master thread or all threads. So for all codes. So can you comment on how good these auto-parallelizing containers are?
So there are certain applications. So the question is, are there compilation strategies that are applicable today, that are in vogue today, that already allow you to efficiently parallelize depending on the algorithmic requirements across small cores, medium cores, and large cores. And my answer is it depends on the domain. So there are certain kinds of application domains such as machine learning algorithms, which are very well tuned. I mean, the runtime systems that run PyTorch code or CUDA code or your TensorFlow code, because the parallelism is so explicitly open that any compiler can see the parallelism in these systems. But trying to optimize a general purpose application code that is not as easy to see what's inside is where I think the challenge has always been. And that will continue to be the case, but I don't think it's easy. Like, for example, pointer chasing is like you don't know where the data is, and it's a real challenge. And so there's a whole host of algorithms that will still not be happy with how they can be parallelized, and therefore it's a battle that has to constantly keep going. And eventually, I suspect what will happen is that there will be domain-specific languages and domain-specific mechanisms to say, okay, this is a graph algorithms. This is what your compiler should do, so it can be explicitly programmed for these systems. And so I think there will come a situation where it will be highly heterogeneous, high levels of heterogeneity, not only in the hardware, but also in your infrastructure, basically compilers and code strategies as well.
Large language models. Well, the bigger shift is happening here.
Okay, so again, for those on the B teams, the question is the low utilization problem permanent, or it actually will slowly get better and better? And I think, again, it is something that is in fact improving, because not everybody is staying constant for my group to continue to make publications. And so clearly there's a substantial amount of effort being produced in all dimensions, including parallelizing compilers and other kinds of strategies that people have been working on. And so the answer is it's not going to be constant. It's going to evolve. But that underutilization problem that I mentioned is more driven by the desire for a company to satisfy its users rather than any other requirement. In fact, if I can make every user 10% unhappy, I can actually just do that consolidation that I was talking about. But that's 10% of the world's, take Amazon, Google, and all of their stocks, and 10% reduction, right? That's the problem that people are going to face. And so I think utilization, or the sort of the mid-range utilization, they may move slightly to the right, more utilization in the systems, but it's not going to somehow go away. But the question you're also asking is, are there other kinds of application domains, for example, ML, machine learning training systems, which are not user-facing? They are just purely run internally. That's a whole different ballgame altogether, and that's a different optimization space that one can work in. But what I was presenting is user-facing systems. That's where I started with Google's and Netflix and things like that.
Let's thank Professor. Let's take this opportunity once again to thank the alum, Murali, Anonymous, for supporting us in the environment and visits of the people.